Section 4.4, the vector nature of Newton's second law. So this is really just a continuation of the last section. And it says the direction and force of acceleration vectors can be taken into account by using x and y components. So this is just as before when we started talking about two dimensions with our motion. We started using the arrows and the vector symbols, but rather than having to work with vectors, which is challenging, we can, instead of having this sum of the forces is equal to mass times acceleration in vectors, we can break it down into the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. And similarly, the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, because it turns out that the horizontal and vertical motions are entirely independent of each other. So we can just focus on whatever forces are in the vertical direction. That will tell us about the vertical acceleration for the y direction. And for the horizontal or x direction, we can just worry about what forces are there, and that will tell us how much acceleration there is in that particular direction. So by very carefully breaking it down into x and y components of force, we will be able to solve more complicated problems than just single dimension problems. So here's an example of a raft. This is another two-dimensional example. So it says a man is stranded on a raft, mass of man and raft, 1,300 kilograms, as shown in the figure. By paddling, he causes an average force P of 17 newtons to be applied to the raft in a direction due east, the positive x direction. The wind also exerts a force A on the raft. The force has a magnitude of 15 newtons and points 67 degrees north of east. Ignoring any resistance from the water, find the x and y components of the raft's acceleration. All right, so our first step is to draw a picture, right? And we could imagine sort of a top-down view of our raft. And it says that his paddling creates a force that is in the direction due east, which is the positive. So cool, paddling, the raft is able to create some sideways force. So I'll add that on here with a label. There's also wind, right? Is wind in the same direction as this paddling force? Not quite, right? What does it say about the wind's direction? It points 67 degrees north of east. So if P is pointing towards east, the positive x direction, we have to go 67 degrees up from that. And that will give us the direction that the wind is acting, A. Maybe I'll go over this with a different color actually, so that we have some contrast here. There we go. So there's our vector A. This is our basic picture, our nice drawing of what we have, right? That we have a raft. And then these two forces act down. It tells us we can ignore resistance from the water, so that simplifies the problem considerably. So what's our next step? Well, our next step is we want to get this to a free body diagram. So I encourage you to go ahead and try that on your own. Make your own free body diagram, and then we'll compare notes in the next slide. Go ahead and pause to make a free body diagram. All right, did you do that? Okay. So let's take a look at the free body diagram. So the raft has been reduced down to this red square. We have P, that force pointing to the right, and A pointing up and to the right, as shown, and they're both pulling on the raft. That's how we draw it, even if technically the paddling is like more of a push. That's okay. We also have drawn in the positive x and positive y directions here, the axis with the raft at the origin of the axis. And one other note here is that this vector A, because it's pointing in both the x and the y direction, in order to use the vector nature of Newton's second law, we're going to want to break this vector A down into its x and y components, right? Into an amount that is pointing purely in the vertical direction, that we would call A sub y, and another piece that's pointing purely in the horizontal direction that we could call A sub x. And by drawing them this way, they are around the 67 degrees, and we can make a little triangle here And so once again, we can get the side lengths by using our standard vector approach of using some trigonometry in order to relate vector A and the 67 degrees to the x and y components. So a sub y, notice, is on the opposite side of the 67 degrees. So we're going to use sine with it. So we use the magnitude of A, or 15 newtons, times sine of 67 degrees. And similarly, for a sub x, we can find it using the cosine of 67, right? This is equal to ax here. That's equal to the magnitude of a, which is the 15 newtons, times cosine of 67. Now, why does this matter? Well, if you allow me to redraw this so it's a little bit clearer over on the side, maybe up here, should be room up here. We have our raft here. Now we know that there's a y component pointing up, this a sine 67. And then we also have two different x components, right? There's an x component of a that's pointing to the right, and that's our a cosine 67. And then we also, once again, have that blue that is pointing to the right, and it is just the 17 newtons. So once we've broken this down into purely x and y components, right, then we're able to connect it back. This is just the x direction, trying in the axis here. And this is the positive y direction. Now we can go back to Newton's second law in component form. And we can just add up all the ones that are in the x direction and add up the ones that are in the y direction. So let's see. Let's try and erase some of this. All right, I want to keep my picture up there, so sorry for all the erasing here. This is where we can add it up, and they put it in a table form to try and make it clearer in these notes. There we go. Almost gotten rid of it all. There we go. Good enough. Okay. So we see that we have the x components of force P and A, and those can be added together in order to calculate the net force in the x direction. So this x component of A, when you calculate this out, it should come out to about 6 newtons, just so you know. So if you add 6 to 17, that's how you get 23. Similarly, the y components we can add up. Well, P doesn't have a y component, right? It's purely in the x direction, so it doesn't contribute anything in the y. But it does have a y component in vector A, of the wind's push. And so you can mathematically calculate this. You'll find it's 14 newtons. So if you add 14 to 0, you get 14 newtons. So this tells us the net force in the x and y direction. Or in other words, we have the sum of the forces in the x and the sum of the forces in the y. Once we know the sum of the forces in the x and the y direction independently, we can solve for the acceleration in the x and the y direction independently. So let's go see that on the next slide. So we see that in the x direction, the acceleration is the sum of the forces in the x divided by the mass, which is 23 newtons divided by 1,300 kilograms, the mass of the man on the raft. So we get an acceleration of 0.018 meters per second squared. Similarly, in the y direction, smaller net force, same amount of mass because it's still the man in the raft. And so we get a smaller acceleration overall. Once we know the acceleration in the x and the y direction, we could draw them in here, where in the x direction, we have a larger acceleration, but there still is some acceleration in the y direction. And so if you wanted the overall acceleration, you could add these up vectorially to get that the overall acceleration is not purely in the x direction, nor is it purely in the y direction, but it is in some combination of the two. So this illustrates how we can start with vectors that are in multiple directions, split them off into purely x and y directions, solve for the acceleration in the x and y directions, and ultimately, if needed, recombine to find the total overall acceleration. And this is much better than trying to work in vector form. You will always want to break it down into x and y components. Cannot stress that enough. So hopefully this opens your minds to the possibility you'll get plenty of opportunities to practice this idea.